Welcome to the last day of our conference. We hope you've enjoyed everything so far. My name is Michelle Rotan, and I'll be your host for this first session. I'm joined by our CTO, Jeff Greene, who was going to present Kafka-fying ISAM. Jeff joined Synergex in 2006, bringing his passion for open source and standards-based technologies with him. His first contribution to our product suite was Synergy DBL integration for Visual Studio. Over the years, Jeff has provided in-depth technical expertise in web services and all things .NET, culminating in the open source Harmony Core project, which helps customers modernize their offerings while leveraging existing investments. Responsible for the technical direction at Synergex, Jeff works to ensure Synergy-based software stays competitive in a rapidly changing technical landscape. Let's get started.
Hello, welcome to Kafka-fying ISAM, where we're going to talk about changing a Synergy program that uses ISAM at the back end very heavily into a distributed application sitting on top of Kafka without actually getting rid of the ISAM parts. So what is Kafka? I am not talking about the 19th century author. It is a Apache Foundation project that was originally started at LinkedIn. It is both a protocol and an implementation. So there's a literal piece of software that is Apache Kafka, and then there's the protocol that Kafka speaks. So all the clients can speak that protocol and the servers speak that protocol, but there are other implementations. Kafka is a distributed system for handling streaming data. So events flow into the system, they get routed out to wherever they're going to go, and you can check back in on those streaming events, but fundamentally it's data comes in, data gets routed, everyone gets what they're supposed to get, and it's durable. There's some language in this space that's potentially interesting. So they use the terms topics and partitions, and that roughly means what we would previously in Synergy sort of world refer to as queues. So if you combine topics and partitions, they're an ordered series of events that happen. They're stored somewhere, they can be replayed somewhere. Within a partition, delivery is ordered. So again, that's a crucial bit of queues. And there is non-destructive support for multiple clients. This is different than something like default configurations of things like RabbitMQ or any of the other sort of queuing servers that exist out there, where an event goes on the queue, it gets consumed once, and then it's no longer on the queue. Kafka allows each client to consume the queue independently of what the other clients are doing. So we're talking here about distributed systems, and so there's new problems. There's things that people use distributed systems for. There's reasons why we care. So distributed systems they're going to give you a new set of coordination problems. If I have a couple of different nodes and I need to say, no, I'm using this resource right now. You can't book this thing over here. We have to have a way to tell across nodes. Nope, I need exclusive access to that. The way we would have done this in a non-distributed system is probably using things like ISAM file locks. So we need maybe a different primitive there in order to do that same job. So one of the really, really nice things that distributed systems often enable is what's called blue-green deployment. So I can deploy two versions of my software. I can have the old version, and I can have a new version that's running, and I can be testing in production and say, yes, this new deployment is good. before I move everyone over onto being the same deployment. And distributed systems let us do that because they've already tackled all of the difficult problems around coordination across those two deployments and how to share data across those two deployments. Distributed systems also tend to target high availability. So if I have multiple nodes running and I've done a good job at designing my system, it should mean that there isn't a single point of failure. So if there isn't this node must stay up in order for the application to keep working, that should be distributed amongst many nodes. Distributed systems are often associated with sort of cloud native buzzwords. So they can be, an easier management conversation to have with people who are after very buzzwords compliant solutions. They also tend to scale up and down as needed. That's part of that cloud native, like what does that actually mean on the other side? There are some downsides. Oftentimes, you're going to be trading some amount of latency somewhere in the system in order to enable either high availability or more total processing capacity. So I can handle more total events, but the amount of time between the event coming in and the answer coming out may be longer. Depends on how you architect and whether you can hide that latency from the user. Distributed systems also often allow for keeping data geographically closer to the user. So this is one of the ways that sometimes we can trade one kind of latency or lower on another kind. If the user is making 100 requests to read a piece of data and we've reduced the latency on those reads, then they won't really notice that the one time they write a piece of data, the latency increased slightly. So there's a lot of trade-offs here as we're changing the shape of our application. So I'm going to tell you about your path for your application, your Synergy application. How do I become a more distributed application? How do I keep my Synergy code around? How do I leverage Kafka and streaming events in order to make that happen? So right now, today, you're on single node, and we'll dive into that a little bit more in the next slide. But you're on a single node. There's an intermediary step where we have more than one node. So we have replicas, and we have a leader. Leaders are in charge. They can write things. They also can read things, but there can only be one leader. And then there's replicas that are following it. In that sort of setup, you're a little bit limited. Like you're not completely distributed. Only certain things can run on the replicas. Certain kinds of workloads can run on the replicas. You basically have hot standby plus. You get some extra goodies on top of being a hot standby, but fundamentally that's kind of what it is. Later, depending on your application architecture, you can refactor your write operations into a command design pattern and remove a lot of the restrictions around leaders and replicas. So we'll talk more about it later, but those are approximately the layers of Kafka-fying your application. So now we have a single server. All the components are hosted on a single server. This is our one point of failure. You might have other servers that are in the mix, but you probably have one server that is the important one. That runs the actual logic for your application, stores the actual ISAM files, and does all of the coordination, and everyone comes to that one server in order to do all of their work. So there's some some key bits about how your application works. You have direct access to ISAM files, and you have direct access to locks in those ISAM files. And even if you have 100 users on that single server, there's coordination amongst all 100 of them because the ISAM files, they're multi-user. They're on one node, but they support access from multiple applications at the same time. Those are the locks that you have today. So that's where you are today. As we move forward, we have a couple of hard requirements. At least these are what I think are hard requirements. If we're trying to move forward and the answer that we come back with is it's a rewrite, that's not really going to move forward. Those projects tend to not be particularly successful. I think we've all seen that rewrite projects are a quagmire that executives get trapped in and usually don't make it out of. So if the next step involves it's a rewrite, we're not going to start that. We need to think about it harder. Incremental development and deployment is king. If I ship my updates to users regularly in small incremental bits, then I will find out small incremental bugs that I have introduced to the application. Instead of big deployments taking out the entire organization and preventing you from doing your jobs entirely, we have little problems that we can address much faster and are less catastrophic. So, incremental deployment, really crucial to any kind of transformation that we're doing of our application code. Next up, we really can't slow down the users. The feedback that I pretty consistently get from users of DBL-based applications is, it's so fast. I know what I'm doing. I work on my 10 key or I press various buttons through the keyboard and I zip through order processing or I zip through moving this item to where it's supposed to go. Users are able to get what they need done in the application quickly. And so any solution that we're coming up with that's going to transform this application, we can't break that. That's our purpose for being. So it needs to stay no matter what we do. Management has to be willing to sign off on it. Anyone trying to propose a transformation is going to need buy-in from their management. Someone is probably above you making a decision about, is that a good place to spend money? Is that thing too dangerous? So whatever we're coming up with here, it needs to be management friendly. Operations, diagnostics, observability, these things have to be more friendly, not less. So today, in a lot of our applications, because they're on a single node, we can get away with diagnostics that are manually go enable logging on some service, and then go check a file in a folder, read it by hand, and try and diagnose some kind of problem. In a distributed system where you have multiple nodes, this difficulty increases significantly. Those kinds of debug diagnostic tools are pretty ineffective if you've got 5 servers running your application or more, and those servers are distributed around. So we need better tools around operations and diagnostics. We can't accept things getting harder there for diagnostics. And also, I have placed my own hard requirement here that this needs to work on-prem and in the cloud. Some of you out there are going to stay on-prem for the foreseeable future, for cost, for management, for risk aversion. And some of you are going to be in the cloud. And that's just the nature of the world for Synergex, is that some of you will be on one side and some of you will be on the other. So we have the added constraint that if we're telling you about a solution, it really needs to work both on-prem and in the cloud. And what do we have? What's our starting point? We have a couple of building blocks that make our life better. ISAM is really fast. Has the downside that it's tied to the file system, and file systems are not super great distributed, but ISAM itself, real fast. We have I/O hooks. This is really kind of our secret sauce. This is how we enable almost everything that we do. If you haven't seen the power of I/O hooks elsewhere in Synergy code, I would strongly recommend dive into I/O hooks. They make everything that we do here a lot easier. They make everything we do here possible. And you can leverage them in new and interesting ways that are specific to whatever you're trying to achieve. They just make getting creative a lot easier. We have tons of existing code. Whatever code makes up your application, there's probably a lot of it. So we have a bunch of it. It's been around for a long time. A lot of it's tested. Some of it might not be, but in general, it's working for the users. So we have a bunch of code to start with. Synergex has put a lot of effort into supporting containers and Kubernetes in particular. So that checkbox is already checked. And we've been putting a lot of effort into the traditional to .NET migration process. So that used to be a pretty hard task for someone to get through. And we've been focusing on how to make that easier, how to unblock people there, how to make it possible to live in both worlds simultaneously. Marty has a session about this. I would highly recommend that you watch it if you haven't already. But this is made up of compiler enhancements, so the .NET compiler can compile more stuff than it used to be able to. Things that we used to error about, we don't anymore. There's quite a lot of build system enhancements around producing large amounts of main lines that used to be very prohibitive and difficult to do in .NET. And we also have more platform support than we used to. So we work on Windows and we work on Linux currently. And that enables a lot more use cases having that Linux support. And one more prerequisite here, we have some important building blocks that I need to cover. So I'm going to show some diagrams, and we're going to talk about the components and parts that make up the mid-tier answer. And these are some chunks of software that we're making use of. So HashiCorp's console. This thing is actually really made for doing service mesh, but we're using it for coordination and configuration of our services. So it makes a really handy way to do resource locking between the different nodes in your environment, and also getting configuration data down to individual nodes. We are using Red Panda in our implementation. So that is a Kafka implementation. It is using the Kafka protocol. So we use the regular Kafka clients to talk to it. The reason we do that is it's faster. It takes less hardware to do the same job. It does it with significantly less latency. And it's pretty easy to manage and set up. So that's why we ended up with that particular implementation. Docker, get used to it. It's around. Containerizing applications is actually pretty easy. It's really, it's just a Docker file away. I'm not going to demo this here, but WebSSH2 is probably a pretty important building block for you. That lets you put an SSH client into a web shell. So if you were planning on doing legacy modernization, not just for your backend behind the scenes bits, but if you have a requirement that says, we need you to do legacy modernization on your UI, a good way to do that, if your application is currently accessed over SSH or Telnet, is WebSSH2. You get a little window in the browser that has a fully interactive, compliant, VT220 or whatever mode you set it in, SSH terminal, and it's in your browser, and you can put stuff around it. So anytime we talk about web application shells, that sort of thing, that just means that you can build new components, and they can be on the menu, and you can have your existing component launched from the same menu, interacted with in the same sort of place. And it just makes it a lot easier for users in order to, do that migration. And finally, because I have to work on-prem, not just in the cloud, for a few of our scenarios, we've picked, we need an S3 compatible API. So that's the bucket blob store thing from Amazon. And we have a particular implementation of that API that we're using here called SeaweedFS. So our next mode, this is our intermediary step, if you're just coming into this from a single node. So we want to end up with users. They have full access to their RESTful Harmony Core web service. It's running on the leader node. So if they need to do write operations or read operations, it doesn't matter. It's going to work because they're on the leader node. So you might have to do some kind of routing there between the users and the leader or the failover, because only certain kinds of requests can be serviced by whoever is currently in the lead. Users in this mode, they're accessing your application over SSH probably. And so they need to connect into the current leader node. They can go run your application. They do everything in there. The application is going to have direct file system access. So the ISAM files are still on disk in this node, and all of the operations that happen inside the application get collected up. So we use IO hooks to do that interception, and then they get sent off to Kafka via a replication agent. So this is like super SQL replication. So if you watch Steve's presentations around SQL replication and anything that we're doing there in new terms for SQL replication, it's a lot like that. It's just more. It's a next step beyond what we're doing with SQL replication right here in this little box that says replication agent. So all of that replicated data makes it out into Kafka. And then the failover node, the one that's not a leader or follower node, it's connected to that same queue, and its agent is now doing replication. So if you think about the SQL replication case, you have application is putting in updates, and then there's a process that's running over on the SQL server that takes those updates, writes them into the SQL server one at a time until it's, run all the way through the queue. This is like that, except instead of replicating into a SQL server, we're replicating into ISAM files. So if the application is running on this follower node, it still sees ISAM files. They're going to be current ISAM files. The locks that are in those ISAM files, they're separate files between node 1 and node 2. So the locks are not shared between them, but the data is going to be generally identical between the two of them, other than in the short window where that data is traveling through the Kafka queue and into the replication agent. So what does that let you do on that follower node? That gives you read access. So anything where you don't need to write data, anything where you don't need to use those ISAM locks to keep others out in their write scenarios, you can run those on this follower node. And we'll get into next steps where we relax those requirements. But for now, that's what they are in this intermediary step. And finally, in this diagram, we have a little box off into the lower right-hand corner there for console, and that thing is managing configuration. So we're doing coordination in terms of who is the current leader node versus the follower node. Console's doing that job for us. And we're also sending down any configuration to say, think distributed synergy INI file. That's what we're using console for here. So all of this still sits on top of regular ISAM files. As far as the application is concerned, we have not really changed anything in this model. It still opens files that are ISAM files. They're just on disk. It's not going to like XF server or anything over the network. They're regular on disk files. If I'm currently the leader node, I can read and write to local ISAM files to my heart's content. The I/O hooks stick their fingers in between all of the operations that we're doing, and the writes and stores get packaged up and forwarded on to the Kafka topics to be replicated to anyone else who needs those updates. So when I talk about application transparency, that's really what I mean. We are not going to change a bunch of code in the application because you have like a million lines of code, and we really don't want to go find and replacing our way through that. So if we want to make a change, it really needs to not impact the majority of your application. I/O hooks are how we're doing that. So again, here, the flow, once the update is in the Kafka topic, those operations get streamed to any other nodes that might exist in the system, and the agents that are running on those nodes are going to replay all of the operations into their local ISAM files. So if there's a Synergy application running on those nodes, they still have read access to all of those ISAM files. All right, so later. Later is when we've handled coordination issues and we've figured out how to separate write operations in our application into a queue. So rather than the application opening an ISAM file and writing it directly, we want, at least when they're interactive, we want them to create a command pattern object, some kind of instruction, put that instruction in a queue, and let whoever the current leader is run that instruction. Once we've done that separation, it means that we can run the regular application in the follower nodes, and we can run the regular application in the leader node, but the sort of behind the scenes bit that's running the write operations can be separate. It can run based on whoever is right now's current leader node, transparent to the users. I'm going to talk about how we've done that specifically a little bit in the next couple of slides, and definitely in the demo, because the demo application is in this this later phase. So coordination in a distributed system, in this distributed system, involves how do we elect a leader? How do we transition from one leader to another if something happens to them? So follower nodes, they're getting replicated into whatever. They have current good looking ISAM files. And console is managing via locks, distributed locks, who the current leader is. So if one of these nodes gets granted leadership, our order of operations is we have to ensure that we have the latest data. So make sure we've caught up in the replication queue. And then we can become the leader and we can start processing new write operations. So we can consume the pending operations and then send out those replicated updates back to the Kafka topic to make it full circle back to the left-hand side. All of this sounds probably kind of complicated, and Harmony Core helps here a lot. So we have a bunch of code to make this set of scenarios a lot easier. So there are several other problems that we haven't talked about here yet. If I'm doing blue-green sort of deployments where I have multiple versions active in the same system, that means that I need to be able to support migrating schemas of data live. So if I add a field to an ISAM file today on a single node, I'm probably going to take an outage window, run some kind of migration tool, and then bring back up the system and deploy with the new code running. And it's going to make use of that new field in the ISAM file. What do I do in a distributed system with multiple versions running at the same time? We have to do that data file migration live. IO hooks, again, as with almost everything on this diagram, IO hooks make life possible here. We can intercept reads and writes and do your transformation that you used to do in a script. We can do them live in the IO hook. And at the same time, you can actually be running your script on the data that's local to a node. So we can support multiple schema versions at the same time. So Harmony Core also has the actual IO hooks that I keep talking about. So we have some base classes that make it so you don't have to do all of this work. We'll do the intercepts for you and batch up those changes, and all of the important critical bits to do with the IO hooks, they come from Harmony Core. We have snapshot as a concept. So remember, when we're talking about this, we've lifted all of the changes that happen to all of the ISAM files in our system into Kafka. So it's sitting out there in a topic and some partitions, and they're ordered and they exist. And if we started that on day 0 of our application existing, which is infeasible, but if we started that on day 0, Kafka server could contain every change that has ever happened to our application over the last 40 years. It could, if we had a time machine, but we don't. So snapshots are kind of our stand-in there. So those are bundled up, all of our ISAM files at a point in time. They indicate where they start in the Kafka stream. So if someone is a brand new node, they've never seen our data before, they go unpack that snapshot onto their local disk, and then they start reading the replication queue from Kafka at the point the snapshot indicated. So that lets us skip over the theoretical 40 years of events that would have happened in our hypothetical system, and say, I'm going to start right here, and then I'm going to resume processing everything that happens from then on. So bunch of goodies in the snapshot manager. There's command management bits in here. We've used them in the actual application that I have demo. They already had some of this stuff split out. It was already factored out to be running in a queue, so that made it a lot easier. But we still have to have code that does the processing of these commands. And for legacy code, that often means we have to wrap it up in an assembly load context. If you've listened to my presentations over the years, in .NET Framework, that concept that I'm talking about right now was called an app domain way back when, and it's changed names. It's now called an assembly load context. And we use it basically to just isolate legacy code that has lots of globals and statics and things like that, so that we can run those in a multi-threaded environment safely. So there's Harmony core bits to help enable that scenario. And we also have the actual Kafka integration. So the bits that replay ISAM file changes, the bits that collect those into queues and do whatever alerting that we need to for coordination. Those are all built into the Harmony core stuff. So my actual demo application here is RCC. You'll probably remember that was my demo application, though slightly different, at the last conference, where we were demoing running this in Kubernetes. So RCC is used in timeshare industry. We at Synergex, we have source for it. That's why I keep using it as a demo. It was originally intended to support some semi-distributed functionality. So they had the concept of like the resorts run their own server, and then there's like a home office that runs a server. And so they already had a little bit of a split in there. Even though it wasn't usually deployed that way, the code was still architected that way, and that made stuff a lot easier. The version of RCC that we have supports both Windows and Linux, and it's got 30 plus years of effort and functionality in it. So right now, the initial state, if before this transformation, the sort of deployed state out in the world, write operations are queued using ISAM files. So they have a whole bunch of these engines that are processing those queues. They pull records out of the ISAM file. They go process do the instructions, run the code that they're supposed to for whatever that record is. And then they change ISAM files locally on disk. That's how the engines work. Instruction comes in, operation occurs, writes go out. Today, we have a Harmony core-based API that sits on top of that. We have both direct data access via OData, and we have it's kind of a hybrid of traditional bridge and native .NET. But we have logic that's exposed in there as well as just straight data access. The main application, when it's deployed on Linux, is available over SSH. When it's deployed on Windows, it's available over RDP. And resources are coordinated using a convention based on ISAM locks. It today runs on .NET. Generally speaking, that means .NET Framework, but it also runs on .NET 6+. Which is what we're going to take advantage of. So our target state, when we're all said and done, would be containerize everything, bundle everything up, manage all of our configuration in console, so we don't have to do any manual steps on a brand new node. And if configuration changes, it ends up on existing nodes. We want to expose our traditional application in the browser, again, for that legacy modernization conversation. We want to enable load balancing across nodes, and we want to reuse existing code from all of the existing engines. So please make as few changes as possible to the application, and we need to maintain a very low latency user experience. Otherwise, we've really just defeated ourselves. So, time for a demo. Let's see how it's going. All right, so I have 2 nodes here. I have a Windows and Linux running inside WSL. They are not actually sharing files, but they are connected to the same Kafka. So in one window, I have it running in Windows in a terminal, and down here, I have it about to log in a Linux terminal. Do my login, super secret password. Gonna go in now, and we're gonna create a new reservation. Find my good friend Boyce. We're gonna put him at a property in Orlando in a 2-bedroom. Press enter a bunch of times. And his arrival is going to be tomorrow. And it's going to be for 1 night. Some events just popped on the left-hand side there. And we're going to give him our friends and family discount. Press enter a whole bunch more times. And then we'll actually complete the reservation. So it gave us back a reservation number, and we saw a bunch of events happen over in our servers that are processing on the left. So the Linux agent processed the data coming back, and the Windows agent actually processed the event. And we can see that the Windows node has actually updated the ISAM files locally, because we can see our reservation. And we can see in there, Boyce has his friends and family rate and what days he's going to be there. So I can now take that reservation ID, put it into Postman, and I get back, again, the same data. So we're communicating from one node to the other through the Kafka queues, and the engines are just running in the leader node. This is the follower node, and it's the data that's actually getting replicated. So we can see the actual contents of the ISAM file. And the engines are running and producing various diagnostics that we could record if we wanted to tell us how the system is running. What did we just see? So 2 active nodes. One of them's in Linux via WSL. One of them's in Windows. That Linux one could have been containerized. I didn't in this demo, but I do have a Docker file for it. Doesn't really make the demo look any better, but it could be. We had a Harmony Core API that was running on the Windows node. It can run on either one of those nodes, so it's supported on both of them. We had the RCC terminal application running on Windows and Linux, and we showed creating a reservation. So that's all very sort of central. It hits several of the engines that are on the back end of an RCC application, and it's doing all of those things across all of our nodes at the same time. And the most important part about this demo is that very little application code was harmed in the making of this demo. So we didn't have to change very much at all. Because they already write for the engines into queues, we were able to just replace the subroutines that did that right. And everything just kind of works that way. So here's the actual flow of data through the system for the demo. So the application, I went in, queued the request for the booking. That was the first set of events that happened once I picked the human that was going to be making the reservation and told the system what day and for how long they were going to stay there. It starts making the booking. It's not been complete yet, but a couple of events get processed. Those happen in the engines, and a notification comes back to our application saying, yep, the engines did that work. We continue using the application. We put in the additional information. If it were a more complicated scenario, I would have done more than just press enter. But I pressed enter a bunch of times and then said, yep, this reservation is final. And we send that request all the way out. It ends up in the reservation engine and the booking engine. Those do their work, their sort of normal, unchanged set of work. They're working against ISAM files. They don't know that I've changed out from under them this whole Kafka thing. It's application transparent, including for the engines. So they do all their logic the way they always used to. The IO hooks intercept all of that, send those out to Kafka, and then the other nodes in the system get those events and replicate those events into their local ISAM files. So that's how data just flowed through the system in this demo. There are some hard parts here. Things that we ran into while we were converting RCC to sit on top of Kafka. Routing updates unambiguously. That doesn't really say a whole lot, but imagine you have files that have lots of tag fields. So Synergy applications often have these tag fields that indicate I'm really one of these records. I have like 10 different subtypes in the same file. And they use tag fields to identify which of the subtypes they actually are. So in a normal application where you don't have to route updates around anywhere, kind of doesn't matter. They get stored into the ISAM file. But in this world, we have to actually know what that update is in order to put it in the right place in the queue and in order to format it in a friendly way for diagnostics and for other potential consumers of that data. And so imagine a scenario where I have written a record that doesn't actually match any tag fields. Probably no one's ever going to try and read that record in the legacy system. But the Kafka-fied version needs to know everything about that record. And so if you write something that doesn't match any of your subtypes, we can't route that update. And so the system is gonna get angry at us and we have to go fix it. So that happened to us in the RCC code base. It alerted us. We went and fixed it. Catching unintended writes and stores. So the RCC app was already designed to, in 95% of cases, use the engines to do all of their writes. There are a couple of places where they were still directly writing to ISAM files, not from an engine. And there's a certain amount of effort involved in how do you locate all of those places. So code search, certainly a way to do it. That falls over if conventions are not always followed. It gets really hard to do code searches if they're sort of, different everywhere. IO hooks can really help with this. So you can put an IO hook in and say, I am not running in an engine. If someone tries to write an ISAM file, and it's not a temporary ISAM file, like it's the kind that should be shared, I can throw an exception. And that way, I've done a global IO hook registration, and anyone comes in and misuses this process to try and write an ISAM file that they shouldn't, the IO hook can kick it out and prevent it from happening and let us know where that happened so we can go figure out how to fix it. Everything that's replicated needs a unique key. We are doing replication. SQL replication has the same issue. We need unique keys in order to say that record already exists on the destination system. I'm doing an update. If we don't have a unique key, we don't have a way of knowing what record we're actually trying to update. So everything always needs to be at least one unique key, and that's harder in some systems than it is in others. In the RCC code base, that wasn't actually that hard, but your mileage may differ. In order to make all of these IO hook magic bits work under the hood for how to replicate changes, we have to pass a buffer to get GRFA every time we do a read, every time we do a write, and every time we do a store. We are working on some new IO hooks functionality to prevent needing to make application code changes here, really to allow the IO hooks to get in there in more cases and make more changes without having to change the application. Probably the biggest hard part here is we're really talking about a bunch of new tech stack concepts. So you're used to running your application on one node, and you might pull log files off of that with like Splunk or something. And we're now talking about running on multiple nodes, possibly geo-distributed, possibly some of them are on-prem, some of them are in the cloud. How do you manage that? So we are talking about a lot of new management tools. So your observability, your logging tools, your how do I do deployment tools, they're all different. For us, realistically, that probably means at the bare minimum, Docker containers, because those bundle up these deployment concepts a lot easier. And plausibly, we're also talking about something like Kubernetes, so that you can manage the lifespans of those nodes and who can see them and load balancing and all of those goodies. Those just use different tools now rather than a physical load balancer in front. You probably want something that's a Kubernetes-based load balancer getting at your application. And I keep saying it, observability, real important. It is like oxygen in a distributed system. If you don't have observability, you won't be able to breathe. It won't work. You can't have a working distributed system if you don't have good observability, because there are so many nooks and crannies where things can fall over, and diagnosing those things in production environment would be impossible. There's just too many places to look. So failures need to bubble up appropriately, collate appropriately, and correlate. So as requests come into the system, all of the different places that it goes, I need to be able to trace that event all the way from the user asked for a thing to records got written to disk, and this is why. Does this require more hardware? Probably. We're talking about having literal redundancy. So if today you have, in your on-prem data center, you have like a backup node that you don't really use, but it's there in case something goes wrong, you can use that hardware. If you don't have one of those, we're talking about definitely you'll need some more hardware somewhere. Those new pieces of hardware might be smaller. You might not need as big a scale in a single box because now we're a distributed system. You can have multiple nodes that are running and they're working together. So yes, maybe more hardware, hopefully smaller. Easier backups. Yep, you're using more hardware, but we've made backups a lot easier, and we might have removed for you a really expensive piece of hardware. So the way a lot of folks in the Synergy application space get as much availability as they can is with ridiculously expensive storage area network devices. You don't necessarily need that in this world. So you're going to get your availability from the multiple nodes instead of coming from this single point of failure, very expensive SAN. You also have the ability to get geo-redundancy here that's not synchronous. So at least a couple of you out there get geo-redundancy between your on-prem data centers using dark fiber. So you do synchronous requests across them, and because it's your own piece of fiber and the speed of light is real fast, it makes it to the other node, and it's fine, and the SAN is replicating from one SAN to another. But it's really expensive. And this kind of gets to sidestep that. We're a little bit less latency sensitive as a distributed as an actually distributed application, and we let you, because you're in control of that distributed application, you can tweak where the latency shows up and still give a good experience to the user without spending gobs of money on telecoms equipment. So you've got more hardware. That gives us the possibility of not having any downtime at all. We're completely high available for APIs, and very, very low return to operations for direct applications. So if you're using RDP or you're using SSH, the users on the affected node, they will need to log back in again because it's Windows or it's Linux, and if that whole thing goes away, the state of their current running application will go away, and they have to connect back in. The holy grail here is use APIs, use web applications, and then no one knows if their node went away because it was handled gracefully. And with that, any questions?
We've got a few questions here. So the first one is from Adam Gregory. Can you use this along with SQL replication with the same I/O hook?
So the very short answer to that is yes. The slightly longer answer to that is I know the specific conversations that we're having with you are around actually using these building blocks as part of your SQL replication. So for you very specifically, very yes. For others, there might be a little bit more to it because it's a different endpoint for the SQL replicator to be pulling off of. But yeah, as concepts go, these mesh up pretty well.
And the next question from Adam is the RESTful web service on the follower node Harmony Core?
It is. It doesn't have to be. There's not anything inherent about the follower node API stuff being Harmony Core. That could be XF Server Plus if you really wanted it to be. The main deal there is separating write workloads from read workloads. So a follower in the sort of intermediate stage of legmod is it's not, the followers aren't supposed to write. So if you're going to expose APIs or services or something like that off of the follower, they need to be read-only services that are coming off of there.
Okay, great. You guys can continue asking questions into the chat if you'd like. Chuck acknowledges it's a cool demo. He says, I'm assuming it would be pretty straightforward to use a similar technique to stream data to something like Snowflake. We use XFODBC to stream data to Oracle SQL Server. Would this be more efficient?
So the idea is that whatever your destination is for this data, it's going to end up on this event queue streaming thing. And you can have as many consumers of that as you want. And they're not like time limited consumers. The data is going to stay on that stream for however long you configure retention. So you can have a client that is pulling data events off of that queue and putting them into Snowflake. You can have another client that's pulling events off the queue and putting it into Oracle. You can have another client that's our ISAM replication in order to have multiple nodes that have ISAM files on them. It's really mix and match. You can put whatever you want on the other side of the queue and have it get events and have them replicate out.
Gail Lewis, does this provide the possibility of transactions?
So in what we implemented for the RCC demo, those are all transactioned. So the application doesn't really know that we've done that, but we've had some assistants I sort of allude to. They were already designed to handle operations somewhat in isolation. And so we were able to just stick some goodies around the top and bottom of code. So all of those are fully transacted. So if an event comes in and it results in a failure halfway through processing it, we roll back. And it's like the event never happened. And then you have to go mitigate it somewhere. The fact that it failed, it won't automatically succeed again in the future, but it will not have resulted in any changes on disk.
Okay, great. Chris says, I may have missed it, but presumably the communication is bidirectional.
In the example that we have for RCC, the nodes themselves are receiving replication in one direction, and they're sending out write operations to the write engines. And that's their second direction of communication. I know in your particular case, Chris, you're interested in actually replicating ISAM in two directions. And that's slightly different, but it's still the same underlying building blocks. It's not what I'm demoing here, but it uses the same moving parts to accomplish that.
Okay, great. What version of runtime do I need to be on to do this magic?
So this is a .NET thing. At least mostly, this is a .NET thing. And latest runtime is really the target there in order to enable the Synergy.NET running on Linux. So most of the magic that's happening here is, other than the IO hooks, isn't really happening in the runtime. It's mostly happening as libraries that sit over top of that. But the big move is to .NET, which is achievable. Just in case anyone missed Marty's presentation, you can definitely get to .NET, even if you have very crusty code.
Why use Apache Kafka to complement ISAM file storage instead of other distributed event store and stream processing platforms?
So Kafka has Kafka's like it's a protocol, and it's also a chunk of software. And we're actually only using the protocol. So there's an underlying implementation called Red Panda that we're actually using.
and it's really low latency. So that's really the thing that I'm after in this choice, is that the time it takes for an event to make it into the system, get processed, and loop back around to seeing the effects of it is very, very low. It is much lower with this set of choices than with any other combination of software options that I was able to find. So latency. The short answer is latency.
Thanks, Jeff. Why choose scalable event streaming platforms like Apache Kafka over standard messaging queue systems?
So in my earlier answer about SQL replication, I touched on it just a little bit. So regular event queuing system, the event gets processed by one consumer, generally speaking. And once they've processed it, it's gone. And we have, in our use case, we have many, many, many clients. And so all of the nodes are individual clients, and they're consuming items off of it. Just because I've consumed an event once doesn't mean I don't necessarily want to go back and look at it again. I need to know the difference between something that I've processed before and something that is brand new to me. But I still have access to those older events that I've, in theory, already seen. This is really about having multiple clients to the same event stream and having durability for that data, so that if I blow up a node, I can reprocess those events. Like if something catastrophic happens to a node, I can just go point my starting point earlier in the event stream and replay those events onto a new node.
Thanks, Jeff. Does Synergex currently use this Kafka ISAM approach internally?
So we are starting to. It's used in our sort of next gen SQL replication. It's used as an intermediary there. And the demo that you saw in RCC is sort of Synergex internal. So yes.